Hello, I'm Tina DeClerc and I work at the National Energy Research Scientific Computing Center. I am going to talk a little bit about NERSC in general, but more specifically about a new system that we're bringing in right now. A little background on me. I am a department head here at NERSC. I'm responsible for all of the systems, the security and networking, our 24/7 operations, and the facilities. No, it's not working. NERSC is the mission HPC facility for the Department of Energy Office of Science. And what that means is that pretty much if anybody is going to be doing any experiments for the Department of Energy and they need high performance computing facilities, they're probably running at NERSC. We have over 7,000 users, 800 different projects, 700 codes. We run in all 50 states and in 40 countries around the world. Science that is done in our systems is responsible for about 2,000 publications per year. So that's pretty significant. NERSC has a dual mission. We both want to advance science, but we also need to maintain state-of-the-art supercomputing. So when we are bringing in a new system, we collaborate with vendors years in advance of the actual system's delivery and work on all of the new technologies, figure out what's coming up, and typically by the time we've made a decision and the choices that we've made, the components have not yet been built. And we are almost always one of the first sites to actually get these. So it's always a challenge and it's a lot of fun to bring in these systems because there are so many pieces that we have to try to make work. It's a pretty exciting time. We are also very tightly coupled with workflows. So we are starting to do more with experimental and observational facilities. These are the places that actually run like the ALS and things like that. So I'll get a little bit more into that later in the talk. We also provide a lot of software and application help for our users. And again, I'll talk a little bit more about that later when we get more specifically into the system. So we directly support the Office of Science priorities. That means that all of the different sciences are done here. This is everything from fusion, basic energy research, genomics, biosciences, all of those things get done here, climate science. 90% of our cycles are assigned to the DOE for them to distribute among all the different experiments. And that is close to 8 million hours. We have 10% that's set aside for other uses, 5% for ALCC, and 5% for what's called the Director's Discretionary Reserve. And that is used for various things that somebody may need to learn how to use HPC, or this year, for instance, a lot of it was used for COVID research. Just to give you an idea of our roadmap, our Edison system was an XC30, and that we just retired in May of 2019 so that we could start preparing for Perlmutter. And we are currently running Cori. It's an Cray XC40, and there's about 30 petaflop system. Right now, that's our workhorse, and it's the only system we have on the floor until we get Perlmutter running. Perlmutter is right now literally being brought onto the floor, and I'll talk a little bit more about that shortly. We expect it to have about 3 to 4 times the performance of Cori, be able to get that much more work done. And we've already started working on our NERSC 10 system, which we expect to be an exascale system. So I'll just give you a little background on Cori. As I said, it's a Cray XC40. It is made up of 9,600 KNL compute nodes and more than 2,000 Haswell nodes. We have the Cray Aries interconnect, which is got a dragonfly topology. So typically, you would have about 3 hops for any connection that you need to make across the entire system. And we have a burst buffer. This is basically a storage that sits on the compute area so that the ability to get from the burst buffer to the computes is much faster than having to go to the Lustre file system. And the Lustre file system is 28 petabytes with greater than 700 gigabytes per second of I/O. This was the first system that we actually tried to do more to support large-scale data analysis. So some of the things that we added to the system to allow for that capability was to improve the bandwidth between outside of the system to inside the system so that we could stream data from these experimental and observational facilities. We added more virtualization capabilities, such as Shifter and Docker. We run a lot of Jupyter Hub, for instance. And also what this allows is for those customers who have codes that are validated and tested, they can continue to run those in a container and not necessarily have to use our latest and greatest, because we try to keep the systems up to date for both security reasons as well as a lot of times we're fixing bugs that we've run into. We added more login nodes for those other capabilities like Jupyter Hub. And we created a real-time and high throughput queues. So that may not sound like a big deal, but we are so oversubscribed on the system. We generally have a wait time of about 2 weeks for jobs that are just newly put into the queue. So creating something where somebody can say, I want to run right now, actually is a big deal. So we have a small set of nodes set aside for doing that type of work. If somebody needs a larger set of nodes, they'd have to get a reservation. And then we started supporting a very large data analytics software stack. This year, we added GPU racks into Cori, and that is primarily so that our users could start preparing for the Perlmutter system. So this just gives you an idea of how many hours we use. You'll notice that in 2019, we provided 8.8 billion hours to our users. That was because we had Edison still for part of the year. In 2020, we only had 8 billion, but that was because we only have Cori in the mix right now. And capability usage, this is a supercomputer, so we want to run large jobs. And this capability is a metric that we provide to the Department of Energy that says how many jobs we run that are more than 1,024 nodes. Given that there are 68 processors per node on the KNL, that's a huge number of cores and that's the minimum. And we're at about almost 40% of our jobs are running in that range. And all of this is so that we can support all of the science that's done, things like large-scale particle, in-cell plasma simulations, the largest ever quantum circuit simulation, and the largest ever defect calculation from any-body perturbation theories. So this is not my area of expertise. I don't do the science. I try to make sure the systems operate. So I don't have much of the details about those, but I know that it's really exciting work. And just to give you an idea of the data software that we started to support, over on the left shows several of the different packages that we support, and then how many users have started to adopt them. And on the right, you can see that we started out with a fairly low number of users, like less than 50, that were using the data software stacks. By 2020, that number for just TensorFlow had increased to almost 200. And if you include things like PyTorch, the numbers increased to almost 350. So we've had a tremendous uptake in data software use. And now Perlmutter. This is a system we're very excited about. There's a whole bunch of really new technologies that are coming into play. And so it's not been an easy system to bring in, but it has a lot of capabilities that we're quite excited about. Perlmutter was named after Saul Perlmutter, who is the 2011 Nobel Prize winner for physics in the support of the discovery of the accelerating expansion of the universe. And this is the first time we have named a system after someone who is still alive. So that's had its own interesting bits. When we talked to Dr. Perlmutter about naming the system after him, his concern was that people would be mad at him because the name Perlmutter is so long, and when we typically, the login is the name of the system. So what we agreed to is we would say the login could be sol.nurse.gov instead of perlmutter.nurse.gov. So what is Perlmutter, right? It is as I said, it's going to be 3 to 4 times the capacity of Cori. We have one large CPU-only partition, and that will provide basically the similar capabilities to what Cori has. That has 2 Milan CPUs with 256 gigs of DDR RAM. And then we have GPU nodes, and there are 4 A100 GPUs on each one of those nodes that include tensor cores, NV3 links, with high bandwidth memory, and then there's one AMD CPU on each of those nodes as well. We will have over 6,000 NVIDIA A100 GPUs. The unified virtual memory support helps improve the programmability, of those GPUs. The high-speed network is Slingshot, which is an Ethernet-based, high-performance, low-latency network. This has many very new features, and we're just in the process of trying to get this running. It's a bit challenging. Things have been running a little late on that, and so we're just starting to get all of the newer software in it at this point. But this should be very fast, and it has some better capabilities as far as interacting with the site networks because it's Ethernet based. So one of the things that is very different is that in the past, the high-speed network had connected only the compute nodes. In this case, the storage and the login nodes are all going to be connected with the high-speed network. So the overall interaction of the system, we're expecting to be much better. And the Lustre file system is all flash. And to some extent, this was how we are trying to keep some of that performance that we had from the burst buffer, is by using the all-flash Lustre. This will be the largest all-flash file system that they've supported at this point. It has 6 times Core's bandwidth, and it's using the standard cluster store E1000 system from what was Cray and now is HPE. And a lot of these things are also going to help for our data users. The all-flash file system helps with accelerating the workflows. We have the optimized networks, so we're expecting to be able to pull in data very quickly from the experimental and observational facilities. One thing I didn't mention is that we have an interface between the high-speed network and our center. And we are using the newest networking capabilities there with 400 gigabits per second. And we expect that to be able to run the 400 gigabits per second all the way to the border, where we can connect to ESNet, which is also a very high performance network. So we should be able to get a very high performance all the way from the experimental and observational facilities directly into the system. We'll continue to support the analytics stack that we've been supporting for machine learning and data learning softwares. And one of the things that we're really quite excited about is the system software. They've really modernized it. It's cloud-based there, so that provides a lot more capabilities with regard to redundancy and failover sorts of capabilities that exist within that software. And one of the things that I'm very excited about is when you're running a very large system, one of the things that is a problem is we have a test system, and when we get new software, we put it on the test system, we test it as much as we can. You know, you try to simulate having more nodes and things like that, but you can only do so much on a test system. And when you put it onto the system, there have been a number of times where you'll run into issues at scale that there was no way to find on the test system because it's just too small. And with these additional capabilities, you can kind of split the system. You can even allow users to keep running on some portion of the system while you take the other part and install this new software. And if it seems to work well through all your testing, you might even put some test users on there and let them run on it so that you get more of a real workload and get a much better idea of if the software is going to work at scale. And then if it works great, you can roll it out to the rest of the system. And if it doesn't, you can roll back to the previous version, and still you've not really lost that much time. So I'm very excited about some of these capabilities that we'll have with this software. And it will have dedicated workflow management with the interactive nodes. This is just to kind of give a picture of what I was talking about with regard to what's in the system. So we have the A100 GPUs and the standard CPU nodes. We'll have 12 cabinets of each of the GPU and the CPU racks. Those go into this large rack with 8 chassis. We aren't intermixing the GPU and CPU. They'll all have their own racks. And then those will become our Perlmutter system. And one of the things that I haven't talked about are what we call our centers of excellence. We have these in the network, storage, system software, and in the application readiness areas. Because we buy these systems so early, what this does is that it gives us a way to have better interactions with the company prior to the system actually coming on site. So we were actually looking at the designs early on and providing feedback on those, on all the network, the storage, and the system software end of things. We were working directly with the engineers as they were developing the software, and we are actually working directly with the engineers now as we are trying to install this. Because as I said, all of this stuff is really early. We are generally one of the first sites to get all of these things. So there's things that happen and we have to work through issues. And so this close tie that we have with the engineers is one of the things that really makes it special to getting to run here. And the application readiness, this is something we did on Quarry as well. And this is something we do to prepare our users for the newer technologies. In a lot of cases, we've increased the parallelism required on our jobs in order to actually get efficient use out of your codes. So we have basically, we ask our users, we send out, ask them to give us proposals if they are interested in working with us. So we have people from, on Quarry it was with Intel and our site staff, as well as we bring in postdocs to help users improve their codes. So a lot of people are really excited about getting to work on these teams. In this case, we had 14 application teams for simulation, 9 for data, and 5 for learning. So what happens is we typically what we have done is set up like a week long where they are doing really dedicated time to looking at particular areas of the code where they think they can get a lot of parallelism, and then working through and fixing all of those areas. Because of COVID this year, we actually had to kind of switch things up because you could no longer get together. So they extended the period, did shorter sessions, but with longer time in between. So this actually worked out really well because people could make more fixes in between these meetings and made a lot of progress then when they did meet. So we might actually move to something more like that. So there are sometimes some positives with some of these odd things that happen. So this gives you an idea of the speed up that we see. So the yellow line indicates what the performance was when we started. We always do measurements from at the beginning. And this is the speed up that we see on all of the different applications that we're testing. So we also try to get a lot of different types of applications. The goal here is to kind of find if there are some key things that we can provide to all of our users to help them improve their codes, because not everybody can be on one of these special teams. And because we are always trying to provide a lot of capabilities for our users, we have other things that NERSC does as well. We have our community file system. This is the file system. It's more distant from the system, but it has a lot more capacity. So it's kind of more like nearline access to your data. And it's 75 petabytes currently, and that will increase to 150 to 300. We've been doing increments as we go. We also have a HPSS system. So that is our tape backup, and that is for much longer term storage that is integrated into our systems. So we have long term, then you have the nearline, and then typically when they're running jobs, they'll run them off of Lustre because that is so close to the system and you're going to get much better performance off of it. And then in the last couple of years, we also enabled some edge services. So these are for some users who need to have like databases or API portals in order to do their science. This has started out a little slow, but we've had a huge uptake with 90 services deployed in production. So this has been quite useful for our users, and it continues to be something that we will provide. And I've alluded to this. This is the super facility model is where we are trying to basically integrate the experimental and observational facilities data into our systems. one of the primary reasons for doing this is that those facilities are now starting to do um, science that is creating so much data that they don't have the capability in their center to be able to do all the analysis that they need. And in a lot of cases, when they are doing this, they have multiple runs. So they want to basically analyze the data, review the results so that they can make changes for the next run that they're doing. And it's usually very expensive to run these. So the more information they have to fine tune the next run, the better off they're going to be. So the goal is to be able to stream data as they are running these experiments onto our high performance systems so that the analysis can get done very quickly. They can review that and then they'd be ready for their next runs. It's there's a lot of pieces that have to get involved here, such as just getting the data streaming in. So we're working on things like being able to schedule bandwidth through ESNet, through our network, and then into the system. The real-time queues helps with some of that, but those, as I said, are small. So we also have the ability with an API for them to basically create a reservation, and that will allow them to have larger areas of the system if that's needed. And then another area that we need, this just gives you some idea of the different experimental facilities that we are working with. And again, we are trying to make this as varied as possible so that we can find out what the different requirements are and make sure that we have all of the capabilities that are needed for all of the different facilities. But one of the other areas is login. I mean, these facilities have their own logins, and then they have to come to our site. And to stream the data, that means they first have to have logged in. So we're working on what's called federated ID so that we can have one login from their facility that will automatically allow them access to our systems. This is currently in test. We're testing between NERSC and LBL because that's a local site. But we're hoping that this will help improve some of those accessibility issues. So in conclusion, I'd just like to say the mission of the National Energy Research Scientific Computing Center is to accelerate scientific discovery at the Department of Energy Office of Science through high performance computing and data analysis. So everything that we do, all of the systems we build, all of the additional capabilities we provide is to help advance science. And we feel like we're doing that. As shown by the publications, there is a lot of science that is actually accomplished here. And finally, I was asked to respond to this question, and where do you see exascale computing power benefiting energy research the most? I kind of have trouble answering this because of the most. I feel like there are so many applications that are going to benefit from the additional computing capability. For me, climate is one of the easiest ones for me to visualize because you know that there are so many components involved. Everything from the temperature of the ocean to lakes that exist to the clouds and water vapor in the air. There's all of these components that need to be integrated. You've got mountains and so just the land masses themselves. So many components that have to be brought together in order to get a full picture of what's happening. And we've been getting more and more capabilities to pull in more of this data. So you really need those systems that can support that huge amount of information to be able to get a much wider picture of everything. And I think that applies not just to climate, but to many other areas of science as well. Thank you very much.